And we should be here. Hello, welcome back. Good to see you all. Hello to those of you online. Good to see you. If you can't hear me or if there's any other problems, let me know. So, you made it back. Thank you. We can actually get into some lecture and discussion today. Let's see here. First thing, I got some announcements. First, wouldn't you know, I tried to bring a microphone last time, and somehow the microphone didn't take my audio. So the last time's video didn't have anything that's useful in it, unless you want to just see my screen, which doesn't do anybody any good. Today, it looks like it's recording audio, so hopefully it will be up online. But thankfully, we just had the syllabus last time. You can all read that. Not a big deal, right? Cool. Okay, second, not to get all serious, I told you last time that the homework would come out next week. I sort of lied. I made it today. It's not a hard homework. In fact, Icon just released it to you. Let me show it to you real quick, because I don't think you're going to have, many of you may already have done this. Many of you haven't, that's fine, but let me just discuss it real quick. I know it sounds really bad. Homework number 1 coming out on a Friday. However, it's 2 steps. Install Stan, install or log into Argon. Okay, so let me just walk you through it. There's a link to the Stan page in the homework. There's some code to run, and when you're done, just take a screenshot. Getting to Argon's a little bit trickier if you use a Windows machine. Many of you look like you do. You need an SSH client. Has anyone ever used SSH, Secure Shell, before to tunnel into computers? There is a client called Putty, P-U-T-T-Y. It's open source and free. You download it, install it, and gets it through there. But basically, once you log in, to log in, it's as easy as this. If you don't have a Windows machine, turns out if you have a Mac or a Linux machine, it's already built in. But if you type SSH, your Hawk ID, mine is jtemplate, at argon.hpc.uiowa.edu, it does the rest. You'll need to put your Hawk ID password in. I have an SSH thing. Anyway, long story short, you install a program, you connect to this address, you take a screenshot, you're done. You install a different program, you run a little script, you take a screenshot, you're done. I'm giving this to you now because it's not a lot of work, but in Stan's history, particularly when Stan was really new, those of you with Windows machines may have a hard, or it used to be Stan and Windows didn't like each other a lot, right? I think it's gotten better though. So I think it's as easy as following the steps that you see right over here, these steps. But basically we install Stan itself, okay? That's it. I hope that's not much of a lift, but if we give it, I gave it out today because the sooner you have it installed on your machine, the sooner we can play along together with models, okay? And if you can't get it installed, now you have time to find me, right? So email me, come to office hours, find a meeting time, make it work, okay? Okay, how many of you already have Stan installed? Small number, good. That actually makes me feel good. Then most of you are going to be new to this concept. So those of you who have it installed already, maybe you can take a nap, I don't know. Take a screenshot, run this program, take a screenshot, call it good, okay? Any questions? I feel like everybody's very silent today. How bad could it be? It's Friday and we're doing Bayesian statistics. That to me is like Friday. That's, you know, my type of vacation almost. All right, anything else? Let's see. On Monday, you'll have a formative assessment number 1 that comes out in Icon. You'll have till Friday to do it. There'll be just a couple questions. It'll be about today's lecture, okay? Also, our website has slides for next week and a link to the homework, of course. I'm going to be putting a couple chapters from an old book I learned from actually, about sort of the generalized or a unified framework of psychometrics on there. But again, those are more reference than anything else. Just come to class and do it. But they're not available yet because I didn't have the PDF for whatever reason of that book. So, you know, I don't know how people get the PDFs. But I don't want to know. But I have the actual copy, and I'll scan it this weekend. Do you have the McDonald textbook?
Maybe.
Maybe.
Yes.
If it were to show up in something of mine, I'd be really appreciative. If the textbook fairy would just show up. But, sorry. You're getting a little bit of my home life. Were you going to ask a different question? I apologize.
No, I was going to, yeah.
Okay. My home life, not to belabor a point, but my son asked, he was sort of getting on to us about like the tooth fairy starting to lose teeth, you know, and he's like, over the summer, he's like, Mom, Dad, I think there is no tooth fairy. I think it's you because you're acting all sus. And I'm like, what am I acting sus for, man? I'm not acting sus. And he's like, oh, no, totally acting sus. And then a couple weeks ago, we were driving back from vacation, and he's like, Dad, is there a tooth fairy and a Santa Claus? I'm like, no, there's not. So we made up this joke that the tooth fairy, what, you expect some big guy? Hey, Lexi, could you please mute yourself? Sorry, thank you. The tooth fairy is, you know, some big bald head guy comes in the middle of the night, sneaks in your room and gives you money. Like that doesn't seem plausible, does it? Anyway, so. But his world was not shattered by that. It was okay.
Yeah, mine was shattered part of it because once one of my teeth fell out, and for some weird reason, the tooth fairy didn't visit. And then I asked my dad, and he was like, you know, we check again in a bit. and then I check again in a bit, and it's not that the tooth fairy was late, that, you know, that I have the secret. It's that the tooth fairy usually is supposed to leave, you know, kid stuff like, you know, a coloring book or, you know, pencils, rubber, sharpener, stuff like that. But this time the tooth fairy left DVDs for Back to the Future. And that's the movie he'd been wanting me to watch for a while. So yeah, that's when I found out.
So they're like, come on, Dad, I know exactly what's going on. You and the tooth fairy.
Yeah.
Yeah, I try to walk this delicate balance because I'm not a big, I don't want to push all the like stuff on my kid, you know, like all the lies that we tell them. But I want them to be fairly normal. So it's like, what do you believe? Always try to like turn it around. Like Santa Claus. What do you believe? Do you believe in Santa Claus? Do you want to believe? There's nothing wrong in believing. Whatever. It's okay. But
it finally got me to watch the movies, and I like them.
Oh, good. Yeah. No, there's no tooth fairy. Anyway, sorry, I took us off topic. The book fairy. If the book fairy were to show up, I don't know. I'd be pretty happy. Finally, up on Argon, I put a page. I don't know if this is going to help. I don't even know if I'm going to update it. But there's a thing that we're going to find out today that really quickly, as I'm building these lectures and as we're going through, there's a bunch of definitions that go on in this class. And I thought maybe we could put a page together, and if you ever feel enlightened while I'm teaching and you want to help your fellow students, if you see me give a definition, if you just want to add it to this page, everybody should have access. You should be able to edit it to make it work. So if that works, if you'd like to do that, please do. You don't have to. You'll have my gratitude, but that may help. And if I have a chance to do so, I'll try. But it's one of those things where we slowly are adding things as we go. Okay. Any other questions before we begin? Everybody seems so quiet today. I don't know. Long week? Yeah, got it. All right. Okay, we're going to talk about an introduction to Bayesian concepts today. Some of you have taken Bayes classes before, and that's cool. This may be a repeat of some of the concepts if you have. But it does, I'll try to motivate you listening to this a little bit more because you'll have my language for them and my language will be different than everybody else's. We all come about Bayes a different way. Okay? I already spoiled some of the lecture. We're going to talk about Bayesian statistics, posterior distributions, and Bayesian updating. Why not? Sound good? But before we begin, I showed this picture last time. I'm serious. So about me in my history, I've occasionally submitted a few grant proposals, and some, most of them get rejected. That's just how it goes, at least for me. But occasionally I get a little bit of feedback, and it's like, you should put a Bayesian on your Bayesian proposal. It's like, what do you think I am? So from now on, when people go and say that, I'm going to reply with this. I went to the gravesite. Yeah, like I mentioned before, I've been doing Bayes for a long time. I started with Bayesian way back in like 2001, 2002, somewhere around there. My dissertation was in Bayesian statistics. ETS I was part of a project that ETS was funding, Educational Testing Service, and they ended up patenting my dissertation. So I ended up having now 2 patents and 1 pending for Bayes methods. So I do Bayes just for credibility, but if nobody believes me, I'll just show the picture. All right. So let's start. What's Bayesian? I've been trying to think about ways to integrate more active discussion into classes. Anybody want to talk about Bayesian? Shihong.
I think Bayesian consider each parameter as a distribution.
Bayesian is something where each parameter is a distribution. I like that. That distribution, would you call a prior?
It could be prior.
Could be a prior.
Distribution.
That's good. It's good. I'm gonna play devil's advocate. First of all, I don't disagree with you, but I'm gonna pretend like I do. So let me ask you then, if each parameter has a distribution, I ran a regression in LM in R, and it gave me a standard error, and I could form a confidence interval. Isn't that a distribution? Why is that different?
I think the standard error is considered like if you have infinite data set. That's not the real distribution you will have. It's just imaginary.
By the way, if you can't smell, I'm smiling. You can't tell, but I'm smiling because I'm proud of you. Anyway, yes, agreed. Exactly. So you're used to having distribution with parameters. Where do those distributions come from? They come from, in a frequentist sense, where the word frequency comes. The asymptotic distribution, as n goes to infinity, if you're using maximum likelihood or things that are related to maximum likelihood. Least squares regression, for instance, is one of them. The parameters of that model, under, subject to a few assumptions, which we call regularity conditions, the parameters will converge to a distribution. It's a normal distribution. Now, it takes a long time, a lot of n to get to normal, so a lot of times we do a little bit of a smaller sample version. It's a t distribution. But there are distributions before, but the key thing about Bayesian is that you specify the distributions. So if you have a simple linear regression like, where'd it go right here? So let me see if this will work. Y equals beta 0 plus beta 1 x plus error. You collect x, you collect y, you push a few buttons, and whatever your favorite program is, out pops stuff. You don't make any of the decisions, right? However, in a Bayesian sense, what we'd need to say is beta 0 may follow some type of distribution. Maybe it's normal with a mean of 0, a standard deviation of 100 or something like that. Right? So we provide those distributions for it. Anybody else want to talk about what Bayesian is? What's Bayesian mean to you? I don't know.
Are you allowing people allowed to answer too?
Yeah, absolutely. Just 1 second.
Oh, sorry, I can't see hands raised.
Oh, no problem. Let me, yeah, go ahead. Yes, please go ahead online and we'll come to in class. Go ahead.
Okay. So in Bayesian statistics, with frequentist stuff, you get a point estimate. With Bayesian statistics, you get more of a range of possible answers.
Yes. So in Bayesian statistics, once you take the prior distributions and some type of distribution for your data, you combine them and come up with a posterior distribution. So each parameter will have a posterior distribution. Now, you can summarize that posterior distribution and receive something that looks like a point estimate. Right? Most often, we would want to talk about the mean of a posterior distribution being that. But yes, in Bayesian statistics, you typically have a lot more information because that posterior distribution may or may not look like something that you're used to seeing. So that's that. Does that answer your question? For that app?
Yeah.
Okay, so going in class.
Yeah, so I heard that frequent is that's the parameters treated as fixed, and in Bayesian it's a random variable. I don't know exactly what that implies, but another thing I've heard is that they differ in terms of what they mean by probability as well.
Yes. So the point was in frequent statistics, parameters are considered fixed, whereas in Bayesian statistics, they have some type of distribution. And yeah, that's the case. So in frequent statistics, if we were doing this in a non-Bayesian sense, this line right here, this line, we have two parameters in it, beta 0, beta 1. We actually have a third, like the residual variance, right? Sigma squared error, wherever you want to put that. Those are effectively constants, right? Once we know them, they show up there. In a Bayesian sense, we have to define for each parameter a distribution, a prior distribution. And that's where we talk about each parameter having a distribution. That's a synonym to saying each parameter, we specify a prior for each, or we specify each parameter is random, excuse me. Those are all synonymous. The parameter being random, having a prior, and so forth. Synonyms. How are we doing? How many of you have used Bayesian statistics? How many of you have read articles where they use Bayesian statistics? All right, cool. So let me ask another question then, trying to get us to talk. Why would someone want to use Bayesian statistics?
So,
oh, sorry, go ahead.
Yeah, so if you're studying a property or a character that's not by default normally distributed, for example, like psychological disorders or something like this, it's by default it's not normally distributed across the population.
So if you're studying something not normally distributed, I would actually counter that. Again, that's a good answer, but I'm going to put a counter commentary. There's a whole field of statistics that involves non-normal distributions. For instance, generalized linear models, generalized linear mixed models, and then back in the older days, non-parametric statistics were worried about that. So, but I would say, in some cases, Bayesian estimation might be easier when you have non-normal data or non-normal distributions involved. So yes, I'll give you a yes on that. Yes? Well,
I feel like Bayesian data on advantage of Bayesian can estimate different kinds of models, no matter what kind of model.
Yes.
And we need a relatively smaller sample, maybe.
Yeah, I would agree. The comment was the advantage of Bayesian was to estimate different types of models. And actually, that's where I came to Bayesian statistics myself. I'm interested in general in multidimensional psychometrics, psychometric models. Multidimensional IRT you may be familiar with. My research was also in diagnostic classification models, another multidimensional method. And when I started doing work in diagnostic models, there wasn't any software to do this. In fact, my introduction to Bayesian was not through a class, it was through a paper, which you will read later in the semester. And by the way, you're now our research assistant, we're gonna pay you, go and fix the Markov chain Monte Carlo code in Fortran that's broken. Here you go, good luck, right? Yeah, that was fun. Anyway, actually, it really was a great opportunity, and I learned a lot about it. I don't know that we eventually fixed it, but it was a long time learning it to do so. But we did that. We used Markov chain Monte Carlo because the alternative to use a non-Bayesian sense would have taken the computations were so they sort of grew exponentially so much so that any type of estimation, this again was 2002, was very difficult, if not impossible. It would take forever to do functionally. So another reason why people use Bayesian statistics is that high dimensional problems, become a little bit less computationally intensive. They're still computationally intensive, but we're cutting down on 8 weeks to maybe 8 hours, something like that. That's a good thing. How are we doing talking about Bayes? Yeah. There's a segment of people who think Bayes fixes problems you might have in data sets. Have you ever heard of them? Like if you got small sample size, use Bayes.
Yeah, I've heard about that it fixes multiple testing as well.
Multiple what?
Multiple testing problems.
Multiple testing problems, yeah. If you have multiple hypothesis tests, well, it does because there are really no hypothesis tests in Bayes. So multiple tests, you got to worry about p-values, type 1 error rates. Yeah, none of that matters because we're not going to hypothesis test. We're going to come up with credible intervals and talk about features of data that are a little bit different than the frequentist sense, or non-Bayesian, depending on how you want to call it. Let me talk about the small sample size thing for a second. Has anybody ever heard that before? Bayesian is great for small samples? Well, think of it this way. Why Bayesian might be, actually, oh, hang on one second. Let me finish this thought and I'll get to you online in just a moment. Why Bayesian is good for small samples, or it may be good, comes from where we were talking about that frequentist idea that as n goes to infinity, your parameters converge in distribution to something we know. And part of that involves the standard error, right? The standard error of your beta in regression comes, in a frequentist regression model, comes from asymptotic, what we call asymptotic convergence, right? But in small samples, it's not guaranteed to, that convergence might be very slow, meaning small sample size, you may underestimate how much error there happens to be. You may have problems or miss certain features of your data. So in Bayes, it doesn't rely on that frequentist assumption of convergence. It doesn't say we're going to come up with a standard error based on some theoretical property as n goes to infinity. We're going to instead estimate what we call a posterior distribution, which we'll talk about later today. Online, Nathan.
Yeah, well, I was going to answer, when maximum likelihood doesn't work, then Bayes can help. But then the one thing that I have often questioned is, doesn't it open the door to bias, because even uninformative priors still have a source of information that they're using or assuming. So if you have the wrong posterior idea, then that could cause biased estimates in the future.
So yeah, if you have the wrong, if you have prior distributions the use of priors in Bayesian does introduce a subjective component to what we do. Even uninformative priors can have an impact. However, depending on the type of analysis you're doing, the prior is only one bit of information, and if you have a lot of data, the data will overwhelm the prior. As we get later on into class, we'll have a sort of mathematical basis for making that claim. But the reality of it is, unless you are really, yes, you can use Bayesian statistics to say, I believe the beta 0 on this is 0. And in fact, I'm going to set the prior such that the variance, the mean is 0 and the variance is 0.0001 or something like that, right? That's a very informative prior. And if not a lot of data, your results are probably going to show that. And that's a problem. That is potentially a problem. You can do that. But in the reporting of your Bayesian statistics, you are reporting also the prior distributions you're using. And sometimes actually people think it's a positive to use prior information when you use, bless you, when you develop when you develop an analysis, because that prior information may help you understand a little bit more about the world that you're doing, sort of narrow down the types of options, the results that you might get. Does that help online?
Yeah, well, so is the concept of intractable integrals when Bayes steps in?
In the concept of intractable intervals, there are integrals. There are
integrals.
Integrals, right? Yeah. For some of what we do, particularly in psychometrics, if you are trying to estimate let's say an item response model, a psychometric model where you have binary data Actually, I just made slides about this for next week. We're going to see it next week, but you have a latent variable. To estimate that, you have to integrate out across, in a maximum likelihood sense, you'll have to integrate the latent variable out of the likelihood function. That takes a lot of effort. Now, for one dimension, it's not big, but for lots of dimensions, that effort gets more and more and more. And I'll give you more specifics as we go later in the semester. So the Bayesian idea to come in and build a Bayesian estimator for it turns out does not need that integral. Now, it does need a lot of other steps, a lot of other calculations, but generally speaking, for latent variable models with non-normal data and high numbers of latent variables, a Bayesian solution can work faster, usually does work faster in estimation. So that's and sort of that is tied into the idea where I came to Bayesian statistics with, which was I'm never going to be able to estimate, a 5-dimensional model or a 20-dimensional model or a 300-dimensional model with maximum likelihood. So how am I going to estimate this? Bayes gave a solution. Yes?
So if maximum likelihood, like the mechanism is calculus, what's the equivalent mechanism for Bayes?
For Bayes, it's a Markov chain. Or
No idea what that is.
we're going to learn that.
Great.
We're going to learn that. It is a process by which, instead of trying to figure out in calculus, so in maximum likelihood, calculus is used to find the peak of a function, right? So you can think of, in a lot of calculus, this is sort of a lot of calculus that you do. If you wanted to find the peak of this function, you try to figure out where a line tangent to it was flat. You could test whether that was a maximum or a minimum, and you'd be happy. And that's what the basis for a lot of maximum likelihood happens to be. Now, there are shortcuts. Some problems have closed forms, like in regression, there's a formula. But in most of the psychometrics that we do, there isn't just a formula. So what ends up happening is maximum likelihood is trying to find that peak, whereas Bayes takes a different approach, which is let's try to basically fill in the distribution. Let's sketch what a distribution might look like. So what I mean by that is for each of these parameters, like beta 0 and beta 1, what we're going to do is draw a distribution, and we're going to take samples from their posterior, and we're going to sketch in their values. So rather than try to find the peak or the value of beta 0 that maximizes the likelihood, instead, we're going to just take draws from what we believe the posterior distribution is and sort of form, by brute force, a shape of a distribution. Once we have that shape, that sampled distribution, then we summarize it with the mean.
So sort of like bootstrapping?
Sort of like bootstrapping.
Okay.
Sort of like random sampling of data or of numbers. Just what we're sampling from is in some cases ridiculously complex, but it is a sampling process itself. How are we doing so far? We're just talking before we dive in. I know I'm putting this before I go and talk about like what Bayes is and concepts and stuff, but I want to get us talking. By the way, before next class, I'll do another one of these, and I'm going to show you a survey. I'm going to show you 2 surveys, and we're going to talk about how we think about psychometrics with them, but we'll get there.
Can I ask one more quick question?
Absolutely.
So let's say that you have, you're trying to integrate over a function that is intractable. When we did IRT, we talked about the quadrature points and summation of rectangles as a solution. So is that something that Bayes is doing, or is it more complicated than that?
It's a bit more complicated. So instead of using that, so in most of the Bayes algorithms that we develop and we use, particularly in the Markov chain algorithms, I should back up just a step. Not all Bayes is Markov chains. The ones I'm talking about mostly in this class are Markov chains, so that's where I'm sort of biasing what I'm talking about. So in the non-Markov chain case, the problems are still there. The calculus, the intractable integrals, if you will. But in a Bayes sense, what we're doing instead of trying to get rid of, let's say, the reason why we need that integral in the first place is because random variable, that latent variable. Every time we add a person, we add another parameter, if we think of it as a parameter. And so the benefit of adding more people, as n goes to infinity, is sort of reduced. There's a classic paper by Neyman and Scott back in the 40s or 50s that talk about sort of the problems with getting results that work in broad sense. Put that in quotes, I haven't defined them yet. From situations where you have to add a parameter per person or a set of parameters per person. So in Bayes, what Bayes ends up doing is it basically tries to impute the latent variables. So every step of a Markov chain, instead of integrating across this crazy integral to get it out, we just sample from a person's posterior distribution for the latent variable and plug it in as if we know what it is. And then conditional on it, we do sampling of the other parameters as well too. So it works with a different process to do so. And it's heavily informed by the work from the 1970s of missing data, like the EM algorithm, is classic statistics papers in the 1970s, Dempster, Laird, and Rubin, and then in IRT in the 1980s, early 1980s, with Bach and Aitken about EM algorithms. But it does so with the context that instead of trying to find the set of values that maximize some function, we're going to sample from the set of the parameters posterior distributions instead. All right. So I'm going to move on to the slides now. If we have more discussion, let me go. This was what I wanted this thinking about, dive us in. So now I'm going to talk about Bayesian concepts a little bit more, and maybe some of this will start to make sense, or at least define some of what I just said. Okay? All right. So I found this on Twitter. I hope it's still there. It doesn't. It's not there. I've lost it. Anyway, there is a book, a baby book, about Bayesian. Oh, yeah, you know it?
Well, I'm not so.
It's on TikTok.
TikTok.
Now.
All right, let me just do this. So here we go. This right here, Bayesian probabilities for babies. There's someone you can find reading that book. I thought that was awesome. Well, I don't need to teach class. There's a book, there's a baby book. What do kids know these days, right? By the way, it makes a great present for those of you in the field next time. Next time you know somebody who has a child, maybe we should hand out this book. Have a stash of them somewhere in our library to hand out to everybody with children, right? Anyway, I'll stop there. But if you find it, we can post it later. Basics of Bayesian analysis. So Bayesian statistical analysis refers to the use of models where some or all of the parameters are treated as random components, as we had mentioned before. Each parameter comes from some type of distribution. Now, it comes from really means we actually specify a prior distribution for the parameters themselves. Right? Comes from and is sort of my very colloquial way of describing that. So then, each parameter has a bunch of prior distributions, but sort of the workhorse of the Bayesian statistics is the likelihood function of the data. Right? So let's imagine the regression scenario again. Go back to my regression line. All right, here's our regression line. We may specify a prior distribution for beta 0. We may specify a prior distribution for beta 1 and a prior distribution for the error variance as well. Those are all prior distributions, but there's another key component in this, in that this model itself is trying to work with the distribution of y. That distribution of y is specified by the model itself. We'll talk more about what that happens to be next week, but that's the likelihood function. And it turns out the likelihood function that you know and love from maximum likelihood and the likelihood of the data in Bayesian is the same function, which is the most awesome thing, even though it turns out like the terminology changes. It's the same likelihood. So you have a model actually specifies a likelihood function. That likelihood function is what we use for the data. And that's the core of the Bayesian analysis. So what we end up doing back here, each parameter, the likelihood, if we were to plug in the parameter along with our data, a hypothetical value of a parameter along with our data, we'd see how likely that were to occur. Right? The peak of, or a height of a likelihood distribution talks about how likely something is to occur. So what we end up doing is we tool the likelihood of the data with the likelihood based on the prior distributions, and we form what's called a posterior distribution. The posterior distribution of the parameter conditional on the data. So if you think about it in a Bayes sense, if you come in, before you collect data at all, let's imagine we're going to do a simple linear regression. You haven't collected data once. You could specify priors for your parameters, right? Beta 0 has a normal prior, mean of 0, variance of whatever, 100 or something like that. Beta 1 has a normal prior, mean of 0, variance of 100. You haven't collected any data. What is the prior doing? It's expressing your belief, your current belief of what those parameters happen to be, okay? Or what the distribution of those parameters happen to be. The mean of it being 0 would be like our point estimate. So you'd say, before I collected any data, my best guess about the parameters is the mean is 0, they're both 0. Then we collect data. So what we need to do in a Bayesian analysis is to take the data with its likelihood, combine it with the prior, produce this posterior. Well, that posterior is an updated belief. It moves us from our prior belief to a belief that involves the data that we just collected based on empirical information. So now our point estimate might say, no, the mean of the posterior distribution for the mean for beta 0 is actually 10, right? So now our posterior distribution will look different than our prior. So the final estimates themselves come from the posterior distribution. And there are a couple ways of thinking of that posterior distribution. Posterior distribution is an updated form of a prior. Turns out that's where the term Bayesian updating comes from, right? So we have this study. Before we collected data, we thought the parameters were 0. Now we collected data, we updated our belief. So we have a new posterior. If you wanted to go collect more data, we could use that as a prior, the new belief, the posterior distribution 1 analysis, as the prior for the next analysis, right? And that would update it further. So that is the process that Bayesian statistics works by. Sort of this idea that we're updating our belief from initial values to something that reflects a little bit more a blend of belief and evidence itself. How are we doing so far? Online? No? Okay.
So I have a question. So when you're doing a Bayesian analysis, do you do random sampling until you get to a stable posterior distribution?
Yes. Yes.
Okay.
Yeah, and we'll cover that as we go further. Right. For right now, thank you for posting the video. Let's see if I can do this here. This is the video.
Oh, that's switched.
What? No? I can't hear it. Anyway, that's why.
Bayesian probability for babies. This is a ball. The ball is a piece of candy on a cookie. Yum.
Now, I don't have to go through all this, but here,
Some cookies,
it gets pretty ridiculous.
given
There's
a candy cookie, is 1/3.
Have you seen, how many of you have seen this?
Huh? 1 is greater than 1/3.
All right.
Cookie.
I'm not going to do much more than that. But the point of the matter is, that's it. That's what this lecture is all about. They stole our lecture. No, actually, I'm stealing their book. Okay. TikTok. By the way, I don't do TikTok. I just draw the line there. Everybody else does. I don't. I don't do much social media. All right. So from the posterior distribution is where we take our estimates, our summaries. So we all still want to describe what's going on with data. Turns out the summary statistics of those posterior distributions are what we use in Bayes statistics to say what's happening. You want to know what the regression slope is? Take the mean of its posterior distribution. We want to talk about the uncertainty in the estimate, take the standard deviation of the posterior distribution. There's all sorts of ways the posterior distribution gets used, and it's very helpful for understanding what we do. It's not very different from how we would do frequentist statistics, where we would say we would form a confidence interval around a parameter estimate. In Bayesian, we actually call it a credible interval, but that's a different topic. We'll get there. How are we doing? Cool. So why we use Bayesian methods? We just mentioned this prior to this, but I'll just flip through this quickly. They get used because, I believe, because of the relative accessibility of one method of estimation, MCMC. At least that's how I use them. Other people use them for other reasons, but MCMC, something that physicists and chemists knew about in the 1950s, statisticians started to know about in the 1980s, people in educational measurement knew about in the late 90s, so relatively recent advances in things, made it so that we could take really difficult problems of estimation and solve them pretty quickly. And STAN is neat because STAN isn't built to do psychometrics, but we could use it for that. In fact, we could use it for a whole class, pretty much any class of models, not every class of models. There's a catch that I'm sure that we'll get to in just a bit later in class. But STAN is an MCMC estimation package, and it makes a lot of things go very quickly. A lot of complicated models that wouldn't otherwise be able to be estimated. So I think there are four main reasons. If you have missing data, Bayes has nice ways of imputing missing data. It's called Gibbs sampling. You have a lack of software. You have new models that you've come up with that aren't in software. Or maybe you have philosophical reasons. There are some really strongly adamant Bayesian people out there, sort of like a cult, the cult of Bayes. I label it like the strongly adamant people, these cult-like people, like the Roche people are some type of cult, and the Bayes people are cult. I don't know if we can cross those two cults, never mind. There are some very strong philosophical reasons that people believe in Bayesian statistics. And actually, there are some very strong philosophical reasons that people did not like them. In fact, subjectivity of choosing priors was one of them. So that's why they sort of were slow to come to the forefront of how we do things. So let's talk about some perceptions and issues. Use of Bayesian statistics has been controversial, certainly historically. I was reading recently something, and somebody had a quote from Fisher, you know, the dude who was the F-test guy, among other things, with talking about how Bayes is just not a good idea, or just really, actually, it was beyond that. It was like, it's absolutely don't do this, that type of stuff. So the use of certain prior distribution can produce results that are biased or reflect a subjective judgment rather than objective science. That is a problem. But like everything with science, where subjectivity ends and where objectivity begins sometimes is difficult to find out. So for instance, let's imagine we have categorical data. We have a 5-point Likert item. You know, I ask you, how are you feeling today? Or the item says, I feel good today. And you are asked to pick one of the options. Strongly disagree, disagree, neither disagree, both, right? And we take that very discrete item with 5 choices, and we put that in a linear regression. Maybe we want to predict that based on what you had for breakfast. I don't know, something like that, something silly, right? How many calories you had for breakfast predicts how well you feel at a given time during Bayes class, right? Turns out, put that in a linear regression, that's a subjective choice. You don't think of it that way because a lot of people just use regression, right? But would you want to use a linear regression or a generalized linear regression, like a logistic regression, because there's discrete categories? What would be the best option, right? And so subjectivity actually has a role in a lot of the models that we choose as well, too. But we don't think that way. We submit a paper and the model is wrong, we just say that's wrong. We submit a paper with Bayes, we submit the model also, which could also be wrong. But we also describe what priors we've chosen and why we've chosen them. So we talk about the subjectivity that goes into it. And just like anything else in science, the belief of the result is in the eye of the reader. Right? First of all, peer review is one thing, although peer review is quite flawed. Everybody who reads the paper should be able to see and replicate the analysis and disagree with some of the choices you make. So. But there are other ways of testing it. So let's say I pick a set of priors, and if you're like my experience with the reviewers, you're a reviewer of my paper. Most likely you will say, I don't like your priors. I think you should use these ones. So I can run the analysis differently. How much do the data change with those priors? How much do the results change? Or, excuse me, not data. Results change with those priors, right? There's ways that we can talk about the sensitivity of analysis subject to the priors themselves as well, too. So I think the subjectivity argument is a key one, but with transparency and with trying different values for priors, for instance, we can get around it. Yes?
Is that like regular practice to like try different priors?
No, not in my world. I don't know those in other places, depending on the place. Certainly, some will. My philosophy is not really shared with the dyed-in-the-wool Bayesians, like the cult Bayesians, if you will. Like, they love a good subjective prior. Like, oh yeah, the variance really needs to be this or that. And I'm less that way. I'm much more, I like a very uninformative prior, and they don't like that. But for other reasons, they think you should make judgments about your data. So, but that, if you're worried about the subjectivity, you always have that option. Try it with the prior that you think should be there, try it without a prior, with a very uninformative prior, and see how much results change, right?
Oh yeah, the only reason I ask is because working with my advisor, we run models like 6 different ways to Sunday, and if the results all converge, we're like, yeah, this seems to hold up.
Yep, you could do that, although it becomes you could be running forever, like with the models, so you gotta be careful with that. All right, the other problem with Bayesian is that Markov chain Monte Carlo, that one estimation method, can be really computationally expensive, however you want to call it. Takes a long time to run, lots of calculations, right? Instead of figuring out the peak of a distribution, we're sampling values from it. So if I told you right now, use a random number generator, draw 10 values and tell me what the mean is, how likely is that mean to be accurate? Probably not that likely, right? You need lots of values to come up with a nice sketch of a posterior distribution. So it takes a long time just to get those values. And there's technical things on top of it. When you start a Markov chain, where you start will help govern how far away, how far away you are from the center of that posterior distribution. We'll talk about how long it takes to get there, because the Markov chain will wander around. Like the values we're drawing at first will be nowhere near the center. It may take a while for it to converge to what we would call a steady state, the center of that posterior distribution, where the good draws are found. Yeah.
Is that called burn-in?
Yes, it is.
Okay.
We will learn about that hopefully 2 weeks, or not next week, Psychometric week, Shark week, and then comes MCMC week. All right? But yes, that is the burn-in period. And there are other features with it as well, because depending on the type of algorithm you use, you may have to tune certain features of it. So yes, there's all sorts of phases in the Markov chain that may happen to be present. So back in 2002, we didn't have STAN. We had bugs, Bayesian updating through Gibbs sampling. But it only worked very coarsely. Then there was JAGS, just another Gibbs sampler, which bugs and JAGS very similar. And then now STAN is out in widespread use. But for many, many years, including shortly after programs have come out, people just needed to know how to code MCMC themselves. Like, I learned Fortran, I wrote in Fortran for years. Seriously, I know Fortran, I know. I'm old, but like, it worked, and it worked well for what I needed to do. And so if I needed an algorithm for something, like Lisa and I wrote a paper, I was on a paper for her, 2010, trying to do kind of a linking design, a simultaneous, concurrent calibration, but we had so many items we broke Bilog, like it just wouldn't do it. So we tried M+, and it wouldn't work. So I wrote a Markov chain algorithm in Fortran, analyzed the data, submitted it to a journal, like literally wrote it. And that's, for most people, you're just not going to do that, right? You got things to do, and I got to tell you, it certainly cuts out a time of writing papers when you're writing Fortran code, right? It takes a long time. So not a good thing. So understanding of, the other thing that's sort of gotten in the way is understanding what Bayesian methods have been. Understanding Bayesian methods, what methods exist, has been very limited outside of math statistics. But that's changed now. Like we are in prime Bayesian season now. But up until, I mean, it was even 6, 7 years ago, people were like, I don't know about Bayes. I don't know about that. Now it's everywhere. It's easier to do. People are more open to it. You know, slow with science, it takes a while to get ideas to catch on. So Bayesian methods in the last 20 years have become widespread. I mean, in some fields they were widespread before that, but certainly in a lot of what we do. Any of you, I hate to say this, I'm going to make a statistics class somewhat controversial, but anyone go to 538.com for election forecasting? You know what I'm talking about, that site? Like they would take, anyway, they use Bayesian statistics to come up with a current prediction of who would be a win in an election. And what they end up doing, update, so they have a way in the beginning, have a prior, but every time a poll is released, they update the prior to a new posterior based on that data, based on features of the poll itself and so forth. And then that current value is published on the website, and then another poll comes out, and they do another set of updating, and they update the numbers that are on the website itself. Right? It's a very prime time Bayesian, it's out there, and it's been around. I remember looking at this site, I want to say in 2004, but there were other people, actually maybe 2008. 2004, some people at Princeton, they're still there, were doing election forecasting. So, yeah, sure.
Yeah, I have a comment on the last point. So CS guys, they didn't care about more Bayesian over machine learning. Most of the software using machine learning, they support GPU accelerate, but Bayesian, from my knowledge, no.
Really?
No GPU accelerate.
Yes, that's.
Yeah, recently the STEM support some models use GPU, but
yes.
the function is limited.
Yeah, that's the other thing. A lot of what we could do in Bayes can be broken into smaller problems that run fast over lots of processors. So a lot of the computer science people, like using graphical cards for machine learning, split up a very complicated task into separable parts. Same thing happened with Bayes, but you don't see a lot of support for it, certainly. I'd like to do that in R, like on my own laptop. Like the new Macs came out and had a better graphics card, and I'm like, what's that going to do for me? I'm like, wait a minute, let me just go and use that card to do my calculations. But I haven't gotten there yet. All right, so here's Bayes' theorem. The theorem relied on Bayes itself. Looking at this here, wow, this is a mistake. Give me 1 second here. This is the nice thing. I should be able to fix this. The prior distribution, so let's imagine we have two events, A and B, two distributions. It's very abstract at the moment. We'll put in what these are as we go forward. The posterior distribution, the probability of A conditional on B occurring comes from the probability of B conditional on A times the probability of A over the probability of B, blah, 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 blah. Often it's written with this little symbol right here, like infinity got cut off. That is called proportional to, and the numerator is listed there. Turns out that denominator right here is really hard to calculate that, and it's sort of a constant, so we call that like a normalizing constant. But let me just dissect things here. What we have here is the prior distribution of the event A. Right, that's what we pick and specify in analysis. B is sort of this normalizing constant. We call it the marginal distribution of B. It can be very difficult to do. The distribution B given A is the conditional distribution of B given A. That is the likelihood of the data. This is where we're going to see this type of setup will work in psychometrics. Our psychometric model will be right here, B given A. Our prior distributions will be A. And then finally, when we put this all together, and a miracle happens, that's called convergence, we get the posterior distribution, A given B. And if you sat with a contingency, if you made this like into like two binary variables and sat with a contingency table, you could work out why this is the case if you just look at it, but I'm not going to do that right now. Let's talk about a live Bayesian value. Example, let's suppose we wanted to assess the probability of rolling a 1 on a 6-sided die. Turns out I've got one. Why not, right? Came to class prepared today. So there's our probability of a 1. We could collect a sample of data. I'll do that later with this, but let's say, imagine I rolled it 5 times and I got this. 0, 1, 0, 1, 1. Right? And let's suppose that those are independent tosses of the die. Completely random, independent draws. So the posterior distribution of this probability, right? If I'm a Bayesian, I want a posterior distribution. I want that distribution to tell me, conditional on the data, how likely that probability happens to be across a range of probabilities, right? Probabilities can go from 0 to 1. I want to see how likely all those are. So the posterior distribution I'm working with here is the probability or the likelihood of the probability of a 1 conditional on the data, conditional on all those x's I just observed. So it turns out we can actually calculate this with Bayes' theorem again. Right? So here, the probability, this P of P1 is kind of weird to say, probability of a probability. This is a likelihood function, a posterior distribution of the probability, the likelihood it happens, conditional on the data, is equal to, by Bayes' theorem, or is proportional to the likelihood of the data, conditional on the value of that probability, times the prior likelihood of that probability. Let me make it a little bit more specific here. What is the probability I'm talking about? Turns out, if I take that die, and the only thing I'm interested in is rolling a 1, there's sort of 2 outcomes for every roll, right? Either I rolled a 1 or I didn't. So if we define it that way, the data I'm going to collect are either yes or no. Turns out that follows a very well-known distribution called a Bernoulli, or binomial with one trial. Right? That distribution has a PDF, or probability mass function, right here. What is it telling us? Well, if we knew the probability here, we could tell you the likelihood of the data conditioned on a given probability. So, who wants to guess what the probability should be? Actually, forget it. I'm going to guess for you. 1/6. On a fair die, 1/6 is the probability, right? So we could plug in 1/6 for the probability, which shows up here or here. And then for each one of our rolls, we could plug in the data, and we get a number, right? It's either, if it happened, we get 1/6, and if it didn't, we get 5/6. Right? That's how this works. Because the rolls are independent, I can actually take the product across each of the rolls to come up with what we call a joint likelihood of all the data that we've observed. Right? So if I roll, so here, from this previous example, 0, 1, 0, 1, 1, I can even tell you what those are. It's 0 is 5/6 times 1/6 times 5/6. 0, 1, 0, 1, yeah. 5/6, 1/6, 5/6, 1/6, 1/6. Multiply all those together, you get our likelihood of 1/6 being there, right? Now, you might be like, yeah, I know that's for a fair die, but I know you, Templin, and you're like, to joke about it, I bet you don't have a fair die, right? So someone might say, no, it's probably 50-50 for you or something like that, right? So you put a 0.5 in, and you choose a different value for this, and you'll get a different likelihood, a different value, right? So that's what this likelihood function is trying to give us, how likely that is to occur. So that's Bernoulli. There we go, I just talked about all that. There's our likelihood function. Given the data that we had, for any value of the likelihood, this is what that product returns, the log of it actually. The log of the likelihood and the non-log of the likelihood end up having a peak at the same spot. The y-axis changes, but the shape of it doesn't. So, where would we say the most likely roll of the die would be based on this? This is not Bayesian yet, this is just likelihood. Somewhere right here, right? Actually, it would be right about there, 0.6, because 3 out of 5 rolls turned out to be 1s. Right?
I'm sorry, and this likelihood function is based on our observed data.
That's right. That's the likelihood of the data. That's exactly it.
I might have missed, is there a name for that? Because it's not posterior. It's not
It varies. I just call it the data likelihood. We would also call this the model likelihood.
Okay.
And in the frequentist sense, if we wanted an ML estimate of what the probability happened to be, we would be maximizing that right there. It turns out the ML estimate is the mean of the number of rolls, or the proportion of times I get 1. Yes?
So, can you correct my understanding here? So, I think the likelihood is the joint probability of the data, except for, like usual when we do probability, instead of knowing theta, we treat theta as the variable.
That's right.
And we keep the data fixed, right?
That's right. Yeah, that's the interesting thing about this. A lot of times when we look at distribution functions, we often say, like, we don't know what the data is, but we're going to condition it on a mean. This is the flip. This is saying we observe the data, we have no idea what the probability is. So let's construct a likelihood function to see what the probability happens to be based on the conditional on the data that we've observed.
So same thing as joint probability, except you treat the theta as the variable instead of the data.
That's right. That's right. Yeah. So when you go to, keep doing this, when you go to this function, we've got x to put in it, and we've got p, the parameter, or theta, as you would call it before. So a lot of times, like you said, if depending on where you're coming at this function in statistics, you're like, oh, I know p, what's the likelihood of observing an x, right? If I know p is 1/6, what's the likelihood of observing a 1 on this roll? Well, that's 1/6 or something like that, right? It's a flip. Once we collect the data, we know that. We don't know what p is. Yeah?
So on here you're saying that the rule doesn't depend on previous or future rolls, so it's independent. Is that true of all times you're
That
using
is,
this function?
so I'm making that assumption. I don't have evidence to support it, but that's often what we think about when we take independent, we're thinking we're taking independent roles or sampling people independently. And more specifically, this first term right here, this product, is the nature of that assumption right there, right? If I didn't make that assumption, I'd still have to form a likelihood function, but I couldn't take this basic product across each of the terms. Does that help?
Yeah.
Thank you.
So Bayes more generally doesn't require independent observation. It's more it would manifest here.
Turns out that is true of Bayes or not Bayes. So what we had here was not independent. Maybe this is maybe there's a cluster effect in how people roll the dice. We need a multi-level model for it, right? This would change. Right? This would change. It wouldn't have a product there. It would have some other form to it. Now, what that form is can get kind of messy, and I'll obscure that for right now. But for the product is the mathematical result of the assumption of independence. How's that sound? Of the roles, of the data. How are we doing? How's the pace? Okay. There's this saying, everybody has I don't know why this pops in my head right now. That I had the best plans of this lecture. I made this like in July. I was like that excited to build this lecture. And I had this great plan, and as I'm giving it, I'm like, oh, I should have done that differently. Oh, I should have done that differently. It reminds me of this, it's a Mike Tyson quote, everybody has a plan until they get punched in the mouth, something like that. Like, this is my being punched in the mouth. Like, I should just practice it in front of the mirror next time or something. Anyway, all right, moving on. So let's talk about a choice of a prior distribution. What's the prior distribution? Or the probability? We can pretty much choose anything. Although I will say, we want the prior, well, there are all sorts of priors. In fact, there are priors that are called improper priors that aren't even distributions. That's a little weird. We don't want to get into that. So let's just restrict ourselves to prior distributions where the range of that distribution results in a probability, or a number that goes from 0 to 1. If we do that, then we kind of restrict our distributions. There's a few distributions that range from 0 to 1. The uniform distribution, a continuous uniform distribution. Oops. I'm waiting. 5, sorry. Another sample. And then there's another distribution called the beta distribution. Ever heard of beta? Beta is a messy distribution. But it's actually very convenient for us in this case. Turns out the beta distribution ranges from 0 to 1. It depends on 2 parameters. So oddly, an alpha and a beta, or an A and a B. But if you pick those parameters just right, like a 1 and a 1, you end up getting a uniform distribution, right? So this is the beta distribution. This is its distribution function. What does that do? That tells us if you pick an A or an alpha, if you pick a beta, for any value of the probability, it tells you how likely that is to occur. Right? So all this math down here, ignore that. The main thing to remember about that, by the way, I had to look it up to figure this out, like to type in this slide. So you don't need to remember that. You don't need to. The thing to remember is this prior is going to express our belief in P1. What is our prior belief about what the likelihood of P1 should be, right? So, turns out the mean of the beta distribution is alpha over alpha plus beta. Those are its 2 parameters, right? Those parameters, in a Bayesian sense, are actually called hyperparameters. What? Right? The parameters of the prior distribution are hyperparameters in Bayes. Sort of offsetting that from the parameter of the data likelihood distribution, the probability. Right? So we've got this probability parameter that we really want the posterior of. So we go and give it a prior, but that prior distribution, we have to specify its parameters, its shape, right? Yes?
What do we call the parameters in the posterior?
Just parameters. Estimates, posterior, I don't know, yes. We don't typically have those parameters, turns out, unless, except for some very, very well-defined cases. So we often don't define them as
We're more concerned with the interval.
We're more concerned about the shape. So the posterior distribution we end up summarizing with basic statistics, descriptive statistics. What's its mean, what's its median, what's its variance, those types of things. We don't often characterize it by its parameters. There's one very small, narrow exception that I'm about to hit on in just a bit, but in general, we'll just get this mound of like if we wanted 1,000 draws from a posterior, we'll have a vector or a piece of data in R that's 1,000 length, and we'll be like, what's its mean? We go through all this complicated stuff to get a posterior, and then we take a mean. So the end of it seems nice. So the parameters of the prior distribution are called hyperparameters. That I tried to underline the definitions on here. If anybody wants to add that to our slide, whatever, feel free. The hyperparameter, I just said that. So we can pick, though, values of A and B, or alpha and beta, that correspond to a mean, or our belief that 1/6 should be the value of the probability of rolling a 1. Because we know the mean of that prior distribution is alpha over alpha plus beta. So we could pick, like if we wanted to believe that the most likely value of the mean is 1/6, if we put alpha as 1 and beta as 5, we've just picked the prior distribution where the mean of that will be centered at our belief, right? So there are many choices, right? We could also pick alpha of 100, beta of 500. There's 2 different choices there. What's the difference? It's how strongly we feel in our beliefs. Right? So here, the variance of beta is that ugly function, which I actually have a typo in. My apologies. So if we pick alpha and beta, alpha of 1, beta of 5, we get a prior mean of 1/6 and a variance of 0.02. But if we pick alpha of 100 and beta of 500, we get a prior mean of 1/6 still, but our variance is 0.002. And I'll show this in a picture in just a moment. So one of these priors takes our belief. Both priors inform our belief that 1/6 is the the average likelihood of what we should see for our dice roll of rolling of 1. But one of the priors has a much smaller variance. That's like us saying, I'm really sure in my belief. Right? It's quantifying your subjective belief in it. Yes, shaking your head. The subjectivity's killing you, right? Is that it? No.
No.
Uh-oh.
I'm in the higher education program. We talk about all research is entirely subjective.
Okay,
So,
good.
This is
Okay, is there something else I can help with? Okay, other questions on this so far? Let me just show the plot real quick. The smaller variance means the prior is more informative, by the way. That's an informative prior. That's a very strong belief, is another way of putting that. Informative priors are those that have relatively small variances. Now remember, all priors are subjective, but if I've got two choices from the same distribution, one's a lot more focused than the other, as we'll see in just a moment. Uninformative priors are those that have relatively large variances. Here's the two plots. This is the result, the likelihood function. This is the beta. So we plug in each value of the prior. You'll see the mean of that is right about where 1/6 is. The same thing for the black line. But it's telling us two different things in terms of likelihood for the other values. It's like, yeah, the average is right here. They have the same average. But quickly, with the red line, the one that's our informative prior, we quickly have very little probability, very little likelihood of a belief, of a die roll that was bigger than 0.2 or less than maybe 1.15 or so, right? It quickly shuts off how likely a result is to occur. Now, this is only one part of the story, though, because prior is the plan and data is being punched in the face, right? So we could still pick the wrong prior and have data fix it, so long as we pick a prior that is somewhat malleable. Questions? Okay. Now, it turns out choosing the beta distribution for a prior for this probability is extremely convenient. That's because when we take our data likelihood from the Bernoulli, we can actually come up with an analytic result for the posterior distribution. We can figure out its distribution almost exactly. It is called, the posterior distribution in this case is also a beta distribution. So this is that one narrow case where there's parameters at the posterior that we're going to describe. This is the case. The parameter of the posterior is, the posterior basically says the new A parameter, this is the new one, this is your prior one. So if we put a 1 here as our prior, sum up the number of 1s that you saw, number of successful rolls of a number 1, you get your new posterior output. Same with beta. This is the beta we had before. If we had 5 here, we sum up the zeros, or the number of times we didn't get a 1, subtract it from the total overall number of times we rolled the dice, and we get our new beta.
And that's because those two things are related, right? It's either yes or no.
That's right.
Okay.
So in this one, I welcome the questions, and I'm trying to figure out the pace, that's all. In this one narrow case, this is called a conjugate prior. A conjugate prior is one where the prior distribution leads to the same family of distributions as the posterior. And generally speaking, that makes our life very easy. Because now we know the mean of the posterior distribution, because it comes from beta. It was alpha over alpha plus beta. So once we add our data to it, we can quickly calculate the mean of the posterior. We can quickly form its shape. We don't even need to sample to fill it in. So this is really convenient. This is also really limited. And to figure out how this works, you'd have to do lots of math, right? You'd have to go and plug in all the equations, do some algebra, and then map them onto the distribution that you think it is. In this case, it was beta, which makes a big difference. That exercise is better left to the statistics department. We're just going to use it here. So this is the posterior distribution, conditional on our data. So the black line You see the red line. Remember, the black line went up like this. It's now changed so that its peak is somewhere around 0.3, whereas the red dash hasn't changed very much. And that's the impact of the stronger prior. The stronger prior means that. Yes?
Sorry, what were the black and red again? Black's the...
Black is the uninformative
Yeah.
prior, red is the informative prior. And I'm realizing I'm out of time. So, we're going to continue this on Wednesday. Sorry, I didn't remember what day of the week it is.
What's the LM book in this syllabus?
The book in the syllabus is Levy and Miss-Levy book.
Okay.
And you're welcome to take the first chapters and try to read those. They're very Bayesian specific. That's sort of what I'm covering here, just to get a sense. If this is confusing to you, I totally get it. Hopefully it starts to make more sense as we go through. Right now it's familiarity of the terms. So I will stop here. Thank you for your time today. Thanks for everybody online. Please do email me with questions. And if for those of you who are inclined, our pro seminar first meeting is in 14 minutes, either online or in person, although in person may be very crowded, not enough room. So thank you all. Have a good weekend. See you online.